Welcome to the Deep Dive, where we take complex topics, cut through the jargon, and get straight to the most important, fascinating insights. Today, we're plunging into the fundamental heart of organic chemistry. How chemists, essentially molecular architects, meticulously build incredibly intricate structures, one precisely placed carbon-carbon bond at a time.
That's right. We're going to unpack the very first chapter of a classic advanced organic chemistry textbook, Advanced Organic Chemistry, Part B, Reactions and Synthesis, specifically focusing on alkylation of enolates and other carbon nucleophiles, compote. Think of this as your shortcut, really, to understanding the foundational strategies that unlock the entire realm of modern molecular construction. It's about learning to assemble the most crucial building blocks in organic chemistry.
Okay, so our mission is clear. We're going to break down the major reaction types that allow this molecular alchemy. We'll delve into the clever synthesis strategies chemists employ, reveal the underlying mechanisms that govern these transformations, and explore real-world examples that showcase their power. We'll define all the technical terms plainly, emphasizing the practical synthetic applications that make these reactions so utterly powerful and indispensable in the lab for creating everything from life-saving drugs to advanced materials.
Exactly. By the end of this deep dive, you'll not only grasp these core concepts, but you'll also appreciate the extraordinary precision and ingenuity required to assemble complex molecules atom by atom. You'll see how subtle changes in reaction conditions or the initial starting materials can lead to dramatically different outcomes, and why that level of exacting control is so crucial for chemists aiming for specific, high-value targets. It's truly a testament to humanity's ability to manipulate matter at its most fundamental level. The art of building carbon skeletons. An introduction to alkylation reactions.
Okay, let's unpack this core idea. When we talk about building organic molecules, why is forming new carbon bonds so profoundly fundamental? It seems like such a basic concept, yet it's clearly the starting point for so much incredible complexity. What makes it the backbone, literally, of organic chemistry?
You've hit on the absolute essence of it. It is fundamental because carbon bonds form the very backbone, the entire molecular framework of virtually all organic molecules. Imagine trying to build a skyscraper without any steel girders, or a complex Lego structure where you couldn't connect any of the individual pieces. That's what organic chemistry would be like, without reliable, efficient ways to form these essential carbon connections. From simple solvents that are everyday commodities, to the incredibly complex, often life-saving pharmaceuticals, the intricate natural products that shape our world, and the advanced polymers that constitute modern materials. It all begins with constructing these foundational carbon frameworks. The arrangement, length, and branching of these carbon skeletons dictate the molecule's overall shape, its unique reactivity, and ultimately its function. Without robust methods for creating these linkages, modern chemistry simply wouldn't exist as we know it.
So when we talk about forming these crucial carbon-carbon connections today, what's the basic mechanism driving these reactions? How do these molecular building blocks actually link up at the atomic level?
At its heart, when we're discussing alkylation with the specific carbon nucleophiles we'll focus on today, it's most often an SN2 reaction. If you recall from your chemistry studies, SN2 stands for nucleophilic substitution bimolecular. Let's break that down visually. Imagine you have a nucleophilic carbon. Think of this as an electron-rich carbon atom, perhaps carrying a negative charge, eagerly looking to donate its electrons to form a new bond. This nucleophilic carbon then approaches and attacks an electrophilic carbon, which is on another molecule. This electrophilic carbon is electron deficient, perhaps because it's bonded to something very electronegative, like a halogen, and it's ready to accept electrons. As this new carbon-carbon bond begins to form, the nucleophile simultaneously displaces a leaving group, something like a halide, perhaps a chloride or iodide ion, or maybe a sulfonate, which departs from the electrophilic carbon.
Okay, that makes sense. The nucleophile attacks, the leaving group leaves.
Right. But here's a truly critical detail for chemists. This process involves a characteristic inversion of configuration at the carbon that's being attacked. It's not just a simple attachment, it's a very precise, choreographed movement that effectively flips the three-dimensional arrangement of atoms around that specific carbon as the bond forms.
Like pushing open an umbrella in a strong wind, it flips inside out.
Exactly like that. That's a perfect analogy. And this inversion of configuration is incredibly important for chemists trying to build molecules with very specific 3D shapes. Why? Because the exact 3D orientation of atoms, known as chirality, is often absolutely essential for a molecule's biological activity, especially for pharmaceuticals.
Your body, for instance, is built of chiral molecules and can often only recognize and respond to one specific handedness of a drug. So this precise stereospecific SN2 dance is a foundational tool for controlling molecular architecture. That inversion of configuration really emphasizes the precision required. And who are our main characters, our key players in this bond-forming drama? You mentioned enolates and other carbon nucleophiles in the title. What exactly are enolates and why are they so central to this chapter?
Our primary stars, and arguably the most versatile and widely used players in this field, are enolates. These are essentially negatively charged carbon species. The N comes from alkene, and olate implies an oxygen anion. What makes them particularly stable, and therefore incredibly useful, is that this negative charge, which would otherwise be highly unstable on a carbon atom, is extensively stabilized by an adjacent carbonyl group. That's a carbon atom double bonded to an oxygen atom, right?
Right.
This stabilization allows the negative charge to be delocalized or spread out across both the oxygen and the alpha carbon, which is the carbon right next to the carbonyl. This delocalization makes enolates highly reactive yet also controllable, acting as powerful nucleophiles perfectly poised to form new carbon bonds at that specific alpha carbon position. They are truly the workhorses of many synthetic sequences.
But you hinted at some close relatives. Are there other types of carbon nucleophiles that serve similar roles, perhaps offering different advantages?
Absolutely. Beyond enolates, we also have their nitrogen analogs, which are incredibly valuable in their own right and serve similar synthetic purposes. These include imine anions, sometimes referred to as metalloenamines or anions, and enamines. While their structures might look a bit different from enolates on paper, they involve nitrogen instead of oxygen in the resonance stabilization. They effectively behave as masked carbonyl compounds.
Masked carbonyls.
Yeah, meaning they can be alkylated to introduce new carbon chains, and then crucially, they can be easily converted back into carbonyl compounds through a simple hydrolysis step. This offers chemists different avenues to achieve the same synthetic goal, often with distinct reactivity profiles or, importantly, different selectivity advantages that enolates might not offer.
So if we look at the big picture for someone planning a synthesis, what's the main goal when using these specific players, the enolates and their nitrogen cousins? What kind of new structures are you primarily trying to build?
Well, the overarching goal in synthesis with these specific nucleophiles is to introduce new substituents, most commonly alkyl groups, right next to a carbonyl group. This attachment occurs precisely at what we call the alpha carbon. In the world of retrosynthesis, which is how chemists plan their routes by working backward from a target molecule, you'd look at a complex molecule and identify an alkyl group positioned right next to a carbonyl. You'd then think, aha, I can imagine disconnecting this bond between the alpha carbon and that new alkyl group and forming it via an enolate or related nitrogen nucleophile alkylation. It's a fundamental and incredibly powerful way to extend carbon chains, to build out the complexity of a molecular scaffold, and to set up new chiral centers precisely where they're needed. It's like adding an entire new wing to a molecular building.
And what kind of partners do these electron-rich nucleophiles prefer? What sort of alkylating agents do you need for these SN2 reactions to work effectively and cleanly?
Right. For effective and efficient SN2 alkylation, you need reactive alkylating agents. The gold standard partners are primary alkyl halides and sulfonates. Think of simple ones like methyl iodide, ethyl bromide, or a primary tosylate. These are fantastic because they readily undergo SN2 displacement with minimal side reactions. Allylic and benzylic halides and sulfonates are particularly prized because they are even more reactive thanks to the additional stability of the SN2 transition state that results from conjugation with the adjacent double bond or aromatic ring.
But there must be limitations, right?
Oh, definitely. Here's where the selectivity comes in. Secondary alkylating groups are significantly less reactive. They tend to react much more slowly, and frustratingly for the synthetic chemist, they are prone to unwanted side reactions, particularly elimination reactions, where a double bond forms instead of the desired alkylation.
So you get less of what you want.
Exactly. This can severely reduce your desired product yield. And tertiary or aryl groups, they generally won't work at all with this SN2 mechanism. Tertiary groups preferentially undergo elimination, and aryl groups lack a suitable leaving group in the correct geometry that can be displaced in this fashion. So, careful selection of the alkylating agent, ensuring it's primary or activated, is as important as the careful generation of the enolate itself. This selective reactivity is a fundamental design principle in organic synthesis. 2. Generating and controlling enolates, the foundation of alkylation. Okay, so the very first and arguably most crucial step in making these alkylation reactions possible is actually making the enolate itself. This usually involves a process called deprotonation, where you remove a proton, an H plus F, from a carbon atom that is alpha to a carbonyl group. This specific carbon is acidic because its attached protons are made more acidic by the adjacent electron withdrawing carbonyl.
So the base you choose is absolutely critical here. How do you decide which base to use for this deprotonation? It sounds like you need to be incredibly specific to get the reaction to go the way you want.
You absolutely do, and it's a decision based on fundamental principles of acid-base chemistry. It all comes down to the strength of your chosen base relative to the acidity of the carbon-hydrogen bond you want to break. For chemists, the goal is often complete conversion to the enolate. This means you want virtually all of your starting carbonyl compound to connotatively turn into the reactive enolate. To achieve this, you need a very strong base one that is derived from a much, much weaker conjugate acid than your reactant.
So the base has to be much stronger than this thing is reacting with, essentially.
Precisely. Stated another way, the base you choose must be stronger than the anion of the reactant. Most modern alkylation procedures rely on this complete conversion precisely because it gives you much better regiochemical and stereochemical control over the subsequent alkylation step. If you have an incomplete deprotonation, you end up with mixtures and lower yields. Common workhorse bases that fit this description and are widely used in laboratories today include lithium disopropylamide, affectionately known as LDA.
Ah, yes, LDA.
Yeah.
Hear that one a lot.
Exactly. Then there's lithium hexamethyl disilazide, or LiHMDS, potassium hydride, KH, or sodium hydride, NaNH. These are all powerful non-nucleophilic bases capable of deprotonating even relatively weak carbon acids like simple ketones or esters.
So the pK values, the acidity scale, from what's often presented in the textbook like Table 1.1, are really important here, aren't they? They show the relative acidities and guide your choice.
Absolutely. If you were to look at an acidity scale for common organic compounds, like those typically found in a Table 1.1, what immediately jumps out is how dramatically certain functional groups can influence acidity. For instance, you'd notice how groups like nitro groups, NO2, additional carbonyls, COR, and nitrile, CN, significantly increase the acidity of adjacent CH bonds, often by many, many orders of magnitude. Knowing these relative acidities is absolutely key to picking the right base to ensure your deprotonation goes to completion and to understand why certain functional groups are so good at stabilizing these reactive carbanions.
And this wasn't always the case, right? Historically, chemists used weaker bases.
That's right. Historically, less strong bases like alkoxides were once the only option. They could only be used for compounds with two strongly stabilizing groups, like beta-diketones or malanates, which have pKa values around 913. Reactions were often sluggish and incomplete for simpler compounds. But then the advent of stronger amide bases like LDA in the 1960s truly revolutionized the field. These highly basic, often sterically hindered amides with pKa values around 30-35 allowed chemists to convert even simple monofunctional ketones and esters, which are much weaker acids, with pKa values typically in the range of 20-27, entirely to their enolates. This was a complete game changer for synthetic efficiency and control, opening up a vast new array of reactions that were previously impossible or incredibly inefficient. It transformed synthesis from an art of trial and error to a much more predictable science.
Here's where it gets really interesting, especially with unsymmetrical ketones. My understanding is that you can potentially form two different enolates, depending on which alpha proton gets removed. How do chemists deal with that challenge, and why is controlling that so important?
That's a brilliant point, and it touches on one of the most elegant aspects of modern enolate chemistry, regioselectivity. This is the challenge of deciding where the deprotonation occurs. Do you remove a proton from the alpha carbon with fewer substituents, or the one with more? The ingenious part is that we can control this outcome through either kinetic or thermodynamic conditions, which essentially means prioritizing either the fastest reaction pathway or the most stable product.
Okay, let's dive into that. What's the fundamental difference between kinetic and thermodynamic control in this context of enolate formation?
Let's start with kinetic control. This is all about speed and the path of least resistance. To achieve this, you typically use a very strong, often bulky base like LDA or LiHMDS. You perform the deprotonation rapidly and irreversibly, usually at very low temperatures, around -78 degrees C.
Dry ice temperature.
Exactly, dry ice acetone bath conditions. Under these conditions, the base preferentially removes the least sterically hindered proton. This leads to the formation of the less substituted enolate, because accessing that proton and forming the new bond is faster. For example, if you look at diagrams of typical reactions, like those often seen in Scheme 1.1 of the textbook, it clearly shows this preference. With methyl ketones, like 2-pentanone, kinetic deprotonation almost exclusively forms the enolate where the proton was removed from the methyl group, leaving the double bond between the carbonyl and the less substituted carbon. Bulky bases like lithium tetramethylpiperidine, or LTMP, exaggerate this effect even further because their large size makes them even more sensitive to steric hindrance, forcing them to attack only the most accessible proton.
Like a large person grabbing the easiest apple.
Precisely. It's the easiest one to reach quickly.
So kinetic control is about the easiest, fastest proton to grab. And thermodynamic control, that sounds like it's about stability, allowing time for things to settle.
Exactly right. For thermodynamic control, you allow the enolates to equilibrate. This is often achieved by having an excess of the starting ketone present, which allows for reversible proton transfer between the ketone and the enolates. You might also use a product solvent like an alcohol, or by adding certain additives like hexamethyl phosphoric triamide, HMPA, which can help promote equilibration. The mixture will then eventually settle into a state that favors the more substituted enolate.
Why is that one favored?
Because the more substituted an alkene is, and remember, an enolate has a double bond, the more stable it generally is due to hyperconjugation. That's where electron density from adjacent CH bonds helps stabilize the double bond. This concept is also beautifully illustrated in Scheme 1.1.
Are there exceptions, though? Chemistry always seems to have exceptions.
Oh, absolutely. And they highlight the subtlety of molecular interactions. For example, with 3-methyl-2-butanone, the less substituted enolate is actually slightly favored even under thermodynamic conditions. This is likely due to significant steric interference that would destabilize the more substituted enolate if it were to form. Another interesting case is 1-phenyl-2-propanone, where the acidifying effect of the phenyl group causes the conjugated enolate to be favored under both kinetic and thermodynamic conditions. For cyclic ketones like 2-substituted cyclohexanones, kinetic deprotonation typically occurs at the C6-methylene group, while the more substituted C2 enolate is slightly favored at equilibrium. A 3-methyl group can also significantly influence kinetic deprotonation by blocking access, but has little effect on the thermodynamic stability. This powerful ability to choose between speed and stability is a cornerstone of selective synthesis, allowing chemists to tailor the reaction to get exactly the desired enolate isomer.
It sounds like there's another layer of complexity here, which I find really fascinating. E and Z isomers for enolates themselves. So it's not just about where the double bond forms, but how it's oriented in 3D space around that double bond. That seems like an almost unbelievable level of control to achieve at the molecular scale.
You've perfectly captured the nuance. It is an extraordinary level of control. Many enolates, particularly those derived from unsymmetrical ketones or esters, can indeed exist as geometric isomers around their double bond. These are designated as E or Z isomers, much like with regular alkenes, where the enolate oxygen is always given a high priority for assignment. The stereochemistry of these enolates can dramatically influence the outcome of subsequent reactions, especially when new chiral centers are being formed later.
Can you give an example of how this easy control works?
Sure. Take 2-pentanone, for example. When its enolate is formed by deprotonation at C3 with LDA and THF, you typically get a certain ratio of ZE enolates. But here's where it gets truly ingenious. If you add hexamethyl phosphoric triamide or HMPA to the solvent...
HMPA again.
Yes, that useful additive. The ratio shifts significantly to favor the Z-enolate. What's happening is a fascinating interplay of solvent and metal ion.
So the metallication and those additives like HMPA play a huge role beyond just how fast the reaction goes. They actually dictate the molecular shape.
Indeed. It's truly fascinating how a seemingly small change in solvent or additive can have such a profound effect on the fundamental structure of the enolate. HMPA, for instance, is excellent at solvating the lithium ion. It essentially wraps around the positive lithium ion, effectively loosening the lithium ion's tight coordination to the enolate oxygen. In the absence of HMPA, the deprotonation is thought to proceed through a relatively rigid cyclic transition state where the lithium ion coordinates tightly to both the carbonyl oxygen and the incoming amide base. This rigid structure typically favors the E-enolate because the larger alkyl group on the enolate can adopt a more pseudo-equatorial position, minimizing steric hindrance.
Okay, less crowding.
Right. But with HMPA, the lithium ion is more strongly solvated by the additive, weakening its interaction with the enolate oxygen. This shifts the transition state to a looser, more open one, which then actually favors the Z-enolate. It's like releasing a tightly wound spring, allowing it to relax into a different preferred shape.
And it's not just HMPA, right? Other things affect this.
Definitely not just HMPA. Even common inorganic salts like lithium halides, such as Liber, can significantly alter the EZ ratios, often leading to a stronger preference for the E-enolate, as seen with 3-pentano. This suggests incredibly complex interactions within the reaction mixture, involving not just the solvent but also the counterions. Detailed NMR studies and even breathtaking X-ray crystallography images, like those published and often found in textbooks in Figure 1.1, reveal how these small changes in solvation and aggregation translate into big differences in enolate structure and reactivity. These images reveal fascinating hexameric clusters of enolates in solution, where multiple lithium ions are clustered around a central bromide, and enolate oxygens bridge between lithium ions. It's like a tiny, intricate molecular scaffold.
Wow, actual pictures of these things.
Yeah, it's incredible. Such structural details are absolutely key to understanding the observed selectivity. A quick glance at a summary like Table 1.2 for stereoselectivity for various esters and ketones under different conditions will quickly show you that while LDA often favors E-enolates for esters, HMPA can completely flip that to Z-selectivity. This level of control, just by tweaking an additive, is a testament to clever chemical design.
And what about those tricky alpha-beta-unsaturated ketones, or enones? Do they follow the same rules for enolate formation, or do they add yet another layer of complexity because of that pre-existing double bond?
They absolutely add another fascinating layer of nuance, showcasing how context changes reactivity. For these compounds, kinetic deprotonation typically occurs at the alpha prime carbon. That's the carbon adjacent to the carbonyl that is not part of the existing carbon-carbon double bond. This preference is largely due to the polar effect of the carbonyl, which makes those alpha prime protons more acidic and therefore faster to remove. However, if you allow for thermodynamic control, meaning you let the enolates equilibrate, the system will shift to favor the enolate corresponding to gamma carbon deprotonation.
So further away from the carbonyl.
Yes, because deprotonating at the gamma position creates a fully conjugated system. The negative charge can be delocalized across the oxygen and both the alpha and gamma carbons, which is significantly more stable. This distinction is even leveraged synthetically to convert alpha-beta unsaturated ketones into their less stable beta-gamma unsaturated isomers through controlled protonation of the gamma enolate. This precise ability to control where you form the enolate, either at the alpha prime or gamma position, is incredibly valuable for setting up subsequent transformations in complex syntheses.
This brings us to another profoundly important aspect, making one specific mirror image version of an enolate. This concept is called enantioselectivity, and it's critical in drug discovery. How do you achieve that when you're simply deprotonating a molecule? It sounds like you're literally picking a handedness at the molecular level.
You've hit on one of the grand challenges and triumphs of modern asymmetric synthesis. You achieve that extraordinary feat by using chiral bases. These are asymmetric bases, meaning they possess a specific three-dimensional handedness or chirality themselves. They are designed to differentiate between two chemically identical but spatially distinct hydrogens on a molecule. These hydrogens are called enantiotopic hydrogens, for example. The two alpha hydrogens on something like cis-2,6-dimethylcyclohexanone or 4,2-butyl-cyclohexanone. By selectively removing just one of these enantiotopic hydrogens, the chiral base generates an enantioene-enriched enolate. You get a clear preference for one mirror image of the enolate over the other.
So it's literally like a molecular hand guiding the reaction to pick just one side. That's an incredible concept for such tiny molecules.
Exactly, that's a perfect analogy. These reactions depend on incredibly subtle differences in the transition states, the fleeting, high-energy molecular arrangements as the reaction progresses. The chiral base approaches the ketone, and because of its own specific three-dimensional structure, one pathway for deprotonation to form a certain enantioene-enriched enolate will be slightly lower in energy and thus faster than the other. It's a very small energy difference, but enough to dictate the outcome. Some clever examples involve lithium amides designed with specific chiral features. For instance, for 4 substituted cyclohexanones, computational studies have proposed specific transition structures where the chiral base, sometimes in concert with an additive like a chloride ion, guides the deprotonation. You can even achieve this through kinetic resolution, which is a related but distinct strategy where chiral base preferentially reacts with one enantiomer of a racemic ketone, leaving the other enantiomer behind in high purity.
So you purify by reacting one away faster.
Exactly. It's all about designing that subtle, three-dimensional interaction to favor one specific outcome, which is revolutionary for pharmaceutical synthesis, where specific enantiomers are often the only active form of a drug.
Fascinating. But what if deprotonation isn't the best way to get the specific enolate you want, perhaps because of competing side reactions or unfavorable equilibria that lead to mixtures? Are there other methods to generate these elusive enolates with high control?
Definitely. While direct deprotonation is the primary method, chemists have developed several powerful alternative strategies to generate specific enolates, particularly when absolute regio control or milder, more selective conditions are desired. One very powerful alternative is the cleavage of trimethylsilyl enol ethers or enol acetates. These are stable, neutral precursors that can be prepared separately, often with exquisite regiochemistry control, and then, crucially, converted into highly reactive enolates precisely when needed. They can be cleaved by reagents like methyllithium, various alkoxides, or most impressively, tetraalkylammonium fluoride.
Fluoride, how does that work?
The fluoride method is particularly effective because it forms an incredibly strong silicon-fluorine bond. That bond formation provides a powerful thermodynamic driving force for the reaction, making it highly efficient even under mild conditions.
And can you prepare these silyl ethers themselves with regiochemical control, or do they just form mixtures during their initial synthesis?
Yes, absolutely. That's the beauty of it. You can achieve regioselective silylation of ketones directly. For example, by using LDA at low temperatures, around -78 degrees C, along with trimethylsilyl chloride, you can immediately trap the kinetically preferred enolate as it forms, preventing it from equilibrating to the thermodynamic isomer.
So you lock it in place before it can change.
Precisely. This locks in the desired regiochemistry. Even more hindered bases, like the lithium amide derived from chioctyl T-butylamine, can give exceptional selectivity for the less substituted silute enol ether. Textbook examples, often depicted in Scheme 1.2, illustrate these precise methods, including catalytic approaches using silanes with platinum or boron catalysts, which offer even milder and more environmentally friendly routes to these versatile intermediates.
Now, what about reducing existing double bonds to make enolates? That sounds like a really creative and indirect way to control things.
It is indeed a fantastic and highly strategic approach, particularly for alpha-beta-unsaturated ketones, commonly known as enones. By selectively reducing the carbon-carbon double bond of an enone, you simultaneously generate an enolate anion. Lithium ammonia reduction is a classic and very powerful example of this. The true genius of this method is that the starting enone dictates the exact structure of the resulting enolate, giving you precise control over where the new bond will ultimately form. This allows chemists to build complex structures from readily available starting materials. This transformation can even be achieved with silanes as reductants, often catalyzed by transition metals like platinum, leading to highly specific silyl-enol ethers that can then be cleaved to enolates. These reductive methods, alongside the conjugate addition of organometallic reagents to enones, are incredibly valuable for setting up a precisely defined enolate for subsequent alkylation, circumventing potential issues with direct deprotonation.
So once you've gone to all that effort to generate your perfect enolate, does the solvent you choose for the actual alkylation step matter at all for how fast or efficiently the reaction goes? Or is it just a matter of dissolving your reactants?
Oh, it matters immensely, far more than just dissolving a reactants. The rate of alkylation of enolate ions is incredibly sensitive to the solvent in which the reaction is carried out. If you look at comparative data, perhaps in a summary like Table 1.3 from the text, which shows the relative rates of reaction for the sodium enolate of diethyl and butyl malonate with N-butyl bromide in various solvents, the differences are astonishing. You'll see that polar aprotic solvents like dimethyl sulfoxide or DMSO and dimethylformamide DMF dramatically accelerate these reactions compared to non-polar ones like benzene.
How much faster are we talking?
DMSO, for instance, is 1,420 times faster than benzene, and DMF is 970 times faster. That's not a small difference. It's a game changer for reaction speed and efficiency.
Wow. Why is that such a huge difference? What makes these specific polar aprotic solvents so special that they can speed up reactions so dramatically?
It all comes down to how they interact with ions at the molecular level. These polar aprotic solvents have high dielectric constants, meaning they're very good at separating and stabilizing charges, but crucially, they lack hydrogen bonding groups.
No H bonding. That's key.
That's the key distinction. They are excellent at solvating metal cations. They essentially wrap around the positively charged counterion like lithium or sodium, stabilizing it and effectively pulling it away from the enolate anion. But because they don't have acidic protons, they are poor at solvating the negatively charged enolate anion itself. This imbalance helps to dissociate ion pairs and larger aggregates, freeing up a more reactive, bare, and often more pyramidally distorted enolate anion. This naked enolate is far more nucleophilic and thus reacts much, much faster.
So the enolate is sort of unleashed.
Exactly. In state contrast, product solvents like water or alcohols would hydrogen bond strongly to the enolate anion, essentially tying up its negative charge and significantly reducing its reactivity, making it sluggish.
That's a huge difference. What about common lab solvents like THF or DME? They're used all the time in organic labs. How do they fit into this picture?
Tetrahydrofuran, THF, and dimethoxyethane, DME, are indeed ubiquitous in organic labs, and they serve their purpose well. They are moderately good at solvating metal cations, using the lone pairs on their oxygen atoms to coordinate to the positive metal ion. However, because they have lower dielectric constants compared to DMSO or DMF, they're less effective at fully separating ion pairs and preventing the formation of larger aggregates. In fact, some truly fascinating X-ray crystallography studies images that reveal the precise arrangement of atoms in crystals, like those often shown in figures 1.2 and 1.3, in the textbook reveal that in these less coordinating solvents, lithium and potassium enolates often exist as complex hexameric clusters.
Hexameric. 6 units together.
Yes, 6 enolate units and 6 metal ions, often arranged in these intricate repeating patterns, almost like tiny molecular Lego structures. The cluster is significantly tighter with lithium ions than with potassium, and this tightness profoundly affects the enolate's hardness and overall reactivity. Harder, more tightly bound enolates are generally less reactive.
So if THF and DME aren't ideal on their own for maximum reactivity, can you boost reactivity in them? Is there a trick to make them work better?
Absolutely. Chemists have found clever ways to enhance reactivity even in these otherwise practical and convenient solvents. Adding small amounts of powerful cation-binding agents like HMPA, which we mentioned earlier, DMPU, T-meta, or various crown ethers helps break up these large aggregates.
Crown ethers, like little molecular crowns.
Exactly. They essentially act as stronger ligands, wrapping themselves around the metal cation, like lithium, pulling it away from the enolate and leaving the enolate anion more exposed and thus more reactive. For example, studies with cyclopentanone enolate showed that HMPA could increase its reactivity with methyl iodide by an astonishing 7,500-fold for a 10-fold excess of HMPA.
7,500 times faster, just from an additive.
Incredible, isn't it? This is because even if the enolate is still part of a smaller aggregate, the active nucleophilic site is now much more accessible. Even the metal counterion itself profoundly impacts reactivity. Magnesium, Mg2+, enolates are generally least reactive, followed by lithium, Li+, sodium, Nat+, and potassium, K+, which is often the most reactive. This order directly reflects the tightness of their association with the enolate. Smaller, harder cations like Mg2+ and Li bind more strongly, reducing the enolate's effective nucleophilicity. This nuanced understanding of aggregation states and cation-enolate interactions is what truly allows for exquisite control in modern synthesis. 3. Alkylation and action. Specific reaction types and examples. Okay, now that we've explored how to generate and control these powerful enolate nucleophiles, let's see these alkylation reactions in action. Let's start with compounds that were historically very important and laid much of the groundwork for this field. These are the highly stabilized enolates, typically derived from beta-dicarbonyl compounds like malonate esters and beta-keto esters.
Why were these specific compounds so special, historically speaking, that they became the first reliable carbon nucleophiles for alkylation? What made them stand out?
They were truly pioneering. They were the first carbon nucleophiles for which chemists could develop reliably efficient alkylation conditions, paving the way for everything that followed. The reason they were special is profoundly tied to their structure. They have 2 strong electron-withdrawing groups, 2 carbonyls adjacent to the alpha protons. This unique arrangement makes those alpha protons remarkably acidic, far more acidic than a simple ketone or ester.
Much easier to pull off that proton, though.
Exactly. This high acidity means they can be fully and easily deprotonated by simpler, less powerful bases like metal alkoxides, for instance sodium methoxide, in alcohol solvents. This made them much easier to handle and react cleanly in the early days of organic synthesis compared to, say, trying to deprotonate a simple ketone, which was a much messier and less controllable process back then.
And the alkylation itself, once the enolate of a malonate or a beta-keto ester is formed, how does that proceed?
Once the enolate is formed, it's a straightforward SN2 process, exactly as we discussed earlier. This means the alkylating agent must be reactive towards nucleophilic displacement. Primary alkyl halides and sulfonates, especially allylic and benzylic ones due to their enhanced reactivity, work beautifully. Secondary alkylating agents, however, are quite sluggish and often lead to moderate yields because of competing elimination reactions, where a double bond forms instead of the desired alkylation.
That pesky elimination again?
Always lurking. And tertiary halides. They give only elimination products, no alkylation via SN2. A clever trick that highlights their versatility is that if you use sufficient base and alkylating agent, you can even dialkylate a methylene group, introducing two new carbon chains at the same spot. You can also perform sequential dialkylations using two different alkyl groups to build up even more complex structures.
It's quite versatile. What about forming rings with these? Can you use intramolecular reactions where the molecule reacts with itself?
Yes, absolutely, and it's a powerful synthetic maneuver. Intramolecular alkylation using dihaloalkanes, where both ends of the alkylating agent have leaving groups, is a fantastic way to form cyclic structures. You can typically form 3 to 6-membered rings using this method. What's truly fascinating, and often exploited in complex syntheses, is the distinct preference for ring size. The formation of 3-membered rings is overwhelmingly favored, with rates orders of magnitude higher than other ring sizes.
3-membered rings form fastest. That seems counterintuitive. Aren't they strained?
They are strained, but kinetically, the proximity and alignment for the SN2 reaction are just optimal for the 3-membered ring transition state. The relative rates of cyclization for alpha-haloalkyl malonate esters can be as high as 650,000 for 3-membered rings, compared to 1 for 4-membered, 6,500 for 5-membered, and only 5 for 6-membered rings. This remarkable selectivity allows chemists to build strained, small rings with high efficiency.
So, practically speaking, what does this initial type of alkylation, the malonate and acetoacetate synthesis, allow chemists to make? What's its enduring legacy in the lab?
These reactions are incredibly versatile for building larger carbon structures, but the real power, and what cemented their place in organic synthesis for decades, comes from the fact that after alkylation, you can easily hydrolyze the ester groups and then decarboxylate the product.
Decarboxylation, losing CO2.
Exactly. Decarboxylation involves heating the molecule, causing carbon dioxide to be lost, and cleanly forming ketones or carboxylic acids. The beauty is that the malonate and acetoacetate carbanions essentially act as synthetic equivalents for much simpler carbanions, like the enolates of acetone or acetic acid, which would otherwise be very difficult or impossible to directly alkylate with good control. This two-step process provides a robust and reliable pathway.
Can you give an example?
Sure. If you look at diagrams of typical applications, perhaps in a scheme 1.3 from a textbook, you'd see clear examples of alkylations and ring formation, like the synthesis of diethyl cyclobutadienic carboxylate. Then, a subsequent scheme 1.4 would show the decarboxylation step, allowing you to make specific acids and ketones with predictable structures. For example, ethyl acetoacetate can function as the synthetic equivalent of acetone to make a specific ketone like 2-heptanone. You can even use dianions, like the dilithium derivative of acetoacetic acid, for direct alkylation and subsequent decarboxylation, streamlining the process even further. These reactions were, for a long time, the bread and butter of constructing complex molecules before more advanced enolate methods came along.
This is where the modern methods really shine, right? Direct alkylation of simple ketone enolates, often without the need for that extra hydrolysis and decarboxylation step. That must be a huge advantage.
Exactly. The development of methods for the stoichiometric formation of kinetic and thermodynamic enolates truly opened the door for direct alkylation of simple ketones, making the process much more efficient and atom economical. And a crucial aspect here, particularly in complex molecule synthesis and especially for pharmaceuticals, is stereoselectivity. When you form a new stereogenic center, a carbon atom with 4 different groups attached, leading to a specific 3D handedness, you want to control its precise 3D arrangement. The general principle, based on decades of observation and computational modeling, is that the electrophile, the alkylating agent, approaches perpendicular to the enolate's double bond. The key to selectivity then becomes minimizing steric hindrance. The electrophile will always choose the path of least resistance, approaching from the less hindered of the two faces of the enolate.
So it avoids bumping into things.
Essentially, yes.
Yeah.
The degree of stereoselectivity then depends entirely on how much steric differentiation there is between those two faces. It's like guiding a robot arm to pick up an object from a crowded table. It will always go for the clearest path.
Can you give us some concrete examples of how this steric control plays out in real molecules? How do chemists use the existing shape of a molecule to their advantage?
Certainly. Think about cyclohexanones, which are six-membered rings. For something like 4T-butyl cyclohexanone, which is conformationally rigid due to the bulky T-butyl group locking it in a chair conformation, there's not much inherent steric differentiation around the enolate face itself. As a result, when you alkylate it, you typically get nearly a 1.1 mixture of cis and trans products. There's no strong preference.
But what if you add groups?
Now it gets interesting. If you introduce an alkyl group at the alpha carbon of the enolate itself, that group can subtly distort the enolate, biasing the approach of the electrophile toward the axial direction. Even more pronounced, if there's a methyl group at C3 of the cyclohexanone ring, that group can adopt a pseudoaxial orientation due to what we call allylic strain, a repulsive interaction between a substituent on an alkene and an adjacent alkyl group. This pseudoaxial methyl group then effectively shields one face of the enolate, pushing the alkylation to the opposite, less hindered side. This leads to a strong stereochemical preference, which is incredibly useful for directing synthesis.
What about even more complex cyclic systems like decalones? Do they offer even deeper insights into these subtle stereochemical factors?
Decalone enolates definitely offer even deeper and often surprising insights into these stereochemical factors, highlighting the complexity and beauty of molecular interactions. For instance, the 1-enolate of 1-decalone shows a strong preference for alkylation to give a cis ring juncture.
Cis, meaning the groups are on the same side.
Yes, this is largely due to very subtle 1,4,3 diaxial interactions. The upper face of the enolate in one conformation might present 3 hydrogens in a diaxial relationship to the approaching electrophile, making it severely hindered, while the lower face offers equatorial hydrogens, allowing for a much easier approach. For a trans 2-decalone, axial approach to the electrophile is generally preferred, and a substituent at C1 can further enhance this selectivity.
Do these molecules always adopt predictable shapes?
Not always. Even the conformation of the enolate itself can be unusual. Some decalone enolates have been shown to adopt twist boat-like conformations rather than the more common chair forms, as seen with decalone enolate 3 in textbook diagrams. This unusual conformation can lead to very specific facial preferences because one face becomes completely shielded, forcing the alkylation from the other side. Computational studies, which model the energetics of these transition states at the atomic level, are invaluable here. They really help us understand these subtle energetic differences, sometimes as small as 1 kilocalorie per mole, but enough to completely dictate the major product, as seen with 5-membered rings and the preference for syn or anti-attack, illustrated in figure 1.4 of the text.
So even tiny energy differences matter hugely.
Absolutely. It's like understanding the subtle tilt of a bowling lane that dictates where the ball will go.
And what about chelation? Can other functional groups within the same molecule influence the stereochemistry by interacting with the metal ion of the enolate?
Yes, chelation can strongly influence stereoselectivity, especially in enolates that have additional functional groups with lone pairs of electrons, such as ethers or alcohols. These are commonly found in complex natural product synthesis where every atom counts. The metal counterion, typically lithium, can coordinate not only with the enolate oxygen, but also with these other electron-donating atoms in the molecule. This creates a more rigid, defined, and often highly organized transition state structure.
Can you give an example from a real synthesis?
Sure. In the synthesis of the promising anti-cancer drug, discodermalate, for instance, a specific lithium enolate with an adjacent methoxy group gave a remarkable 6.1 preference for the desired stereoisomer. This preference was likely due to the lithium ion chelating with both the enolate oxygen and the methoxy oxygen, effectively locking the molecule into a specific shape that directs the incoming alkylating agent. What's truly striking is that using the sodium enolate instead of the lithium enolate gave the opposite selectivity.
Well, just changing the metal flipped the outcome.
Completely. This highlights the critical importance of the metal ion size and its ability to chelate, and thus to precisely direct the approach of the alkylating agent. Scheme 1.5 provides many more of these sophisticated examples, from standard LDA deprotonations to using silyl-enol ethers and enone reductions, all aimed at achieving specific stereochemical outcomes.
Do these powerful alkylation principles apply to other carbonyl compounds beyond ketones, like aldehydes, esters, carboxylic acids, or even nitriles? Or are there specific challenges or adaptations needed for each?
Absolutely. These principles are broadly applicable, but each functional group introduces its own set of important nuances and specific challenges that chemists have cleverly overcome. Aldehydes, for example, are a bit tricky. Their enolates are very prone to unwanted aldol-side reactions.
Galdol reactions, where they react with themselves.
Exactly, where two aldehyde molecules react together instead of one reacting with the desired alkylating agent, leading to messy mixtures. To avoid this, you need very specific, rapid deprotonation conditions, often at extremely low temperatures to suppress side reactions. Alternatively, you can use their nitrogen analogs like enamines or anions, which often offer much better control for aldehyde alkylation, circumventing the aldol problem entirely.
What about esters? Are their enolates as stable and reactive as those from ketones?
Ester enolates are generally less stable than ketone enolates, partly due to the potential for beta elimination of alkoxide, which is an unwanted side reaction. However, they can be successfully alkylated by forming them at very low temperatures using strong amide bases like LDA or like HDMS. Alkylations of simple esters also require these strong bases because weaker ones, like alkoxides, would promote undesired condensation reactions like chelation condensations instead of alkylation. While stereoselectivity in acyclic esters can be low with small substituents, it becomes very high with larger sterically demanding groups. For instance, a beta-dimethylphenolsilyl substituent can create significant steric shielding, leading to more than 95.5 anti-alkylation, which is incredibly useful for controlling chirality in these molecules.
And carboxylic acids themselves, can you directly alkylate them at the alpha carbon, given they have that very acidic carboxyl proton?
That's a great question. And yes, you can. You can directly alkylate carboxylic acids by first converting them into their dianions.
Dianions, two negative charges.
That's right. This involves using two equivalents of a very strong base, such as LDA. The first equivalent of base removes the highly acidic proton from the carboxylic acid group, forming a carboxylate anion. The second equivalent then removes the alpha proton, forming the enolate dianion. The brilliant part of this strategy is that the alkylation then happens selectively at the alpha carbon because that's the more nucleophilic site, even compared to the carboxylate anion. This allows you to introduce new alkyl groups directly onto the carboxylic acid framework with precise regiocontrol, which is incredibly valuable in organic synthesis.
What about nitriles and anides? Are they also amenable to these alkylation strategies, perhaps with their own unique advantages?
Indeed, they are. Nitriles, which have a carbon-nitrogen triple bond, can also be deprotonated at their alpha carbon and subsequently alkylated, provided you use a strong, non-nucleophilic base. Phenylacetonitrile, for instance, is considerably more acidic than acetonitrile, making its deprotonation easier. It has even been employed in the synthesis of drugs like meperidine, where dialkylation was crucial for building the molecular scaffold. And for amides, particularly the enolates of chiral and acyloxyzolidinones, we'll see their immense power in achieving unparalleled enantioselectivity in the next section.
Ah, okay. Looking forward to that.
Scheme 1.6 provides a good overview of alkylations across these various functional groups, including interesting lactone and lactam examples, demonstrating how these core principles are adapted for different molecular contexts.
This is a truly clever trick, forming not just one, but two anions on a molecule to direct reactivity, right? Tell us more about these dianions and their unique advantage.
It's incredibly clever, and it truly highlights the precision achievable in organic synthesis, almost like molecular programming. For 1,4,3-dicarbonyl compounds, such as beta-ketoesters or malanates, you can convert them into dianions by using two equivalents of a very strong base, like an alkylithium, sodium hydride, or potassiumide. Let's take benzoyl acetone as an example. The first equivalent of base will deprotonate the most acidic methylene group, which is the one situated between the two carbonyls. It's highly activated by both. Now here's the trick. The second equivalent of base then deprotonates a different, less acidic site, such as the benzyl methylene group in benzoyl acetone, forming what's called a dinediolate.
And the key benefit of forming a dianion specifically, why go through the trouble of removing two protons?
The crucial part, the real synthetic advantage, is that alkylation of these dianions occurs exclusively at the more basic carbon, which, interestingly, is the less acidic position in the original starting material.
Wait, it reacts at the less acidic spot.
Yes. It seems counterintuitive, but the less acidic site corresponds to the more basic, more nucleophilic carbon in the dianion. This selectivity gives chemists incredible control over regiochemistry. If you were to use only one equivalent of base, alkylation would happen exclusively at the more acidic central position between the two carbonyls, because that's where the enolate initially forms. But by forming the dianion, you effectively direct the alkylating agent precisely to the less acidic but now more nucleophilic remote carbon. This unique regiocontrol is invaluable for constructing complex molecules where you need to attach a group at a specific, less obvious position. Scheme 1.7 provides compelling examples of this regiocontrol, even in incredibly complex syntheses, like a key step in making the powerful antimalarial drug artemisinin, where a sulfoxide group serves to stabilize the anion, and the dianion is alkylated stereoselectively at the less acidic alpha position. It's like having a molecular GPS system to put atoms exactly where you want them. That's a great way to put it. Intramolecular alkylation and enantioselectivity. Advanced control.
We've talked about forming rings with dihaloalkanes reacting with an enolate, but can enolates themselves participate in internal cyclizations, where a single molecule reacts with itself to form a ring? That sounds like a sophisticated dance.
Absolutely. Intramolecular enolate alkylation is a tremendously powerful and elegant strategy for forming 3 to 7-membered rings, which are ubiquitous in natural products and synthetic targets. The key here is that the molecule must fold in such a way that the nucleophilic carbon, the electrophilic carbon, and the leaving group achieve an approximately linear arrangement in the transition state.
Linear? Why linear?
This linearity is a specific stereoelectronic requirement because the pi electrons of the enolate involved in bond formation need to approach the electrophilic center precisely perpendicular to its leaving group for optimal orbital overlap in the SN2 transition state. It's a very precise molecular embrace.
What determines the outcome in these intramolecular cyclizations, especially the size and stereochemistry of the ring formed?
Beyond the general principles that govern all ring closure reactions, like the empirical favorability of 5- and 6-membered rings due to minimal ring strain, the enolate-specific conformation is absolutely critical. For example, consider a specific precursor to cyclohexanone, often referred to as compound 7 in the textbook. This molecule cyclizes exclusively to form compound 8 with a cis ring juncture. This is because the transition state that leads to the cis product is far less strained than the one that would lead to a trans product, which would require the enolate to span a greater distance in a less favorable, highly strained geometry. Many examples show exquisite stereoselectivity based on how existing substituents on the molecule control the precise conformation of the cyclizing chain, effectively steering the reaction toward a specific product.
So existing groups can direct the ring closure.
Exactly. A methyl group, for instance, can steer the reaction, like in the synthesis of the antifungal agent fumagillol, by influencing the preferred conformation of the cyclizing chain, making one pathway significantly more accessible than others.
And what about allylic halides in these intramolecular reactions? Do they behave differently because of the double bond?
They can, yes, and it adds another layer of versatility. Allylic halides can undergo SN2' reactions, where the alkylation effectively shifts the double bond within the molecule as the new ring forms.
SN2'. The attack happens further down the chain.
Essentially, yes. The nucleophile attacks the end of the allyl system, pushing the double bond over, and the leaving group departs from the other end. The same ring size preferences we discussed earlier still play a significant role, with 5- and 6-membered rings generally favored over larger or smaller ones. If you look at Scheme 1.8 in the textbook, you get a fantastic glimpse into these intramolecular cyclizations for both ketones and esters. It includes steps in the synthesis of incredibly complex natural products like quadrone and a large-scale synthesis of a pharmaceutical candidate, cyclopentapyridone I, where inversion of configuration at the electrophilic site was definitively confirmed, reinforcing the SN2 nature of the reaction. These intramolecular reactions are truly an elegant way to build complexity and create rings.
This is where we get into making one specific mirror image, or enantiomer, of a molecule. This is absolutely crucial for pharmaceuticals because different enantiomers can have wildly different biological effects. One might be therapeutic, the other toxic. How do we achieve this with enolate alkylation? It seems like magic.
It's certainly a pinnacle of modern synthetic chemistry, and it's not magic, but truly ingenious design. We achieve this by using chiral auxiliaries. These are special, pre-existing chiral groups, meaning they have their own inherent three-dimensional handedness that are temporarily attached to the molecule we want to build. They act as a scaffold, dictating the stereochemistry of the new bond formation by sterically shielding one face of the enolate.
So they block one side.
Effectively, yes. Once the new bond is formed with the desired stereochemistry, the chiral auxiliary can then be removed, leaving behind a highly enantio-enriched product. It's an incredibly effective and widely used strategy. Think of it like a temporary molecular guide or chaperone, leading the reaction to the desired outcome and then politely stepping aside.
Which auxiliaries are most common and why do they work so well? What's the secret to their success in controlling handedness?
By far, the N-acetylhexylidinones are the most popular and versatile chiral auxiliaries. They're readily available from natural chiral amino acids like valine and phenylalanine, which makes them relatively inexpensive and accessible. When their lithium enolates form, they create rigid, five-membered chelate structures where the lithium ion coordinates tightly to both the enolate oxygen and the carbonyl oxygen of the auxiliary.
Chelation, again, holding it tight.
Exactly. This chelation effectively locks in a specific Z stereochemistry at the enolate double bond. The truly clever part is that the substituents on the oxylidinone ring, for example, an isopropyl or benzyl group, then sterically shield one face of the enolate. This forces the alkylating agent to approach exclusively from the other, less hindered side.
So you can effectively control the handedness of the final product with incredibly high precision, almost like designing a molecular mold.
Precisely. For example, two different N-acetylhexylidinone derivatives, like structures 12 and 13 shown in textbook diagrams, can lead to products with the opposite configuration at the newly formed chiral center. This is because their shielding patterns are reversed. One might shield from the top and the other from the bottom. These reactions typically give excellent diastereomeric ratios, often 95.5 or better, meaning 95% of the product is the desired diastereomer and only 5% is the unwanted one.
And you can separate those.
Yes, since these products are diastereomers, they can be separated by conventional methods like chromatography or crystallization. And after carefully removing the auxiliary, often by a simple hydrolysis or reduction, you can achieve over 99% enantiomeric purity, creating those precious single enantiomer compounds that are absolutely essential for modern pharmaceutical applications, where even a slight impurity of the wrong enantiomer can be dangerous. Scheme 1.9 beautifully demonstrates this, with applications including the enantioselective synthesis of precursors to widely used drugs like naproxen and even complex neurotoxins.
Are there other types of chiral auxiliaries that work similarly, or are the oxazolidinones unique in their effectiveness?
No, there are others that offer outstanding results, showcasing the diverse ingenuity in this field. Pseudoephedrine amides are another powerful class that gives remarkably high enantioselectivity. Alkylation usually happens on the face opposite to the beta-oxybenzyl group, and again, the lithium ion likely plays a crucial role by bridging in the transition state, creating a rigid, controlling environment similar to the oxazolidinones. The beauty here is that both enantiomers of pseudoephedrine are readily available, so you can make either mirror image of your desired product just by choosing the appropriate pseudoephedrine isomer, which is a significant practical advantage for chemists designing drug candidates.
That's handy, being able to make either version easily.
Very handy. Other systems like phenylglycinolamides and trans-2-methyl cyclohexylsulfones also show similar high diastereoselectivity, usually through a combination of steric shielding and sometimes even beneficial pi-p interactions between aromatic rings that further stabilize the desired transition state.
And what happens when these auxiliaries are part of really complex molecular frameworks? Do they still behave predictably, or do the intricate geometries of larger molecules introduce unexpected challenges or outcomes?
That's where we see some of the most surprising and intricate results, truly pushing the boundaries of synthetic control. Take the compact bicyclic lactams, specifically compounds 15 and 16, which are common examples in advanced textbooks. Lactam 15, for instance, is consistently alkylated from its convex or outwardly curved face. And even more remarkably, when successive alkylations are performed, all the new groups add from the same endo or interface, allowing chemists to control the configuration of even quaternary stereocenters, carbon atoms bonded to 4 other carbon atoms with incredibly high precision.
Quaternary centers are tough to make stereoselectively, right?
Extremely tough, but here's the twist. Its close structural relative, lactam 16, astonishingly shows exostereoselectivity. That means alkylation occurs on the opposite face, from the outside, even though the molecules are very similar.
Why the difference?
It comes down to subtle details. Computational studies, which analyze transition state energies and subtle structural differences like the pyramidalization of the enolate itself, are essential here. They help us understand these nuances. These energetic differences can sometimes be just a single kilocalorie per mole, but that's often enough to completely flip the stereochemical outcome in the lab, turning what might seem like an unpredictable mess into a controlled, high-yield reaction. It highlights the immense interplay of subtle steric and electronic factors at the molecular level, making molecular design a true art. V-nitrogen analogs of enolates, expanding the toolkit. Okay, now, let's turn our attention to the nitrogen cousins of enolates. These molecules expand the synthetic toolkit for carbon bond formation, offering unique advantages or overcoming specific challenges that enolates might present. First up are enamines.
How exactly are enamines made, and what makes them useful as nucleophiles? I'm curious how using nitrogen instead of oxygen changes the game.
You typically form enamines by condensing secondary amines with two carbon groups attached to the nitrogen with ketones or aldehydes. This reaction often requires an acidic catalyst and a way to continuously remove the water that's formed, which drives the equilibrium toward the enamine product, essentially pulling the reaction forward.
Gotta get rid of the water.
Right. More modern methods, especially for hindered amines or sensitive aldehydes, use strong dehydrating agents like titanium tetrachloride or involve N-trimethylsilyl derivatives of the amines, where the strong silicon-oxygen bond that forms helps drive enamine formation under very mild conditions.
And how do they work as nucleophiles?
Once formed, the beta carbon of an enamine, which is the carbon atom of the double bond that's further from the nitrogen, is highly nucleophilic. This is because the nitrogen atom's lone pair of electrons is conjugated with the double bond, effectively pushing electron density to that beta carbon, making it an electron-rich site, perfectly ready to react with electrophiles. When an enamine is protonated, for example, it happens directly at this beta carbon, forming an iminium ion, showcasing its electron-rich nature at that position.
So you can alkylate them just like enolates, but with nitrogen involved.
Yes, they're excellent for alkylation, particularly with reactive alkylating agents like methyl iodide, allylic halides, or alpha halo esters and ketones. After the alkylation forms the new carbon-carbon bond, the resulting iminium ion is simply hydrolyzed during the workup procedure, typically by adding water and acid to reveal the desired alkylated ketone.
So you get the ketone back easily.
Exactly. This is the beauty. You use the nitrogen to direct the reaction, and then you easily get back to the familiar carbonyl. Enamines derived from cyclohexanones are particularly useful. For example, the pyrrolidine enamine of 2-methylcyclohexanone predominantly forms an isomer where the less substituted carbon is reactive. This means alkylation happens primarily at that less substituted alpha carbon, which can be synthetically advantageous for preparing specific isomers that might be hard to get via direct enolate alkylation. Scheme 1.co provides illustrative examples, including selective alkylations and even dialkylation.
But are they always the best choice now?
Well, it's worth noting that for highly selective alkylation of simple ketones, modern kinetic enolate methods have largely supplanted enamines in many cases, as they often offer even greater control. Yet enamines still hold a valuable niche for specific transformations, particularly aldehyde alkylation, where enolates can be problematic due to competing aldyl reactions.
Next, the enamine anions. What exactly are these, and how do they compare to both enolates and enamines in terms of their structure and reactivity?
These are the direct nitrogen analogs of enolates, often referred to as metallamines or acylyl anions. They are formed by deprotonating enamines, which are compounds containing a carbon-nitrogen double bond at their alpha carbon using very strong bases like lithium amines. Structurally, they are isoelectronic and structurally analogous to both enolates and allyl anions, meaning they have the same number of electrons and a similar arrangement of atoms around the reactive center. They share many fundamental properties, just with nitrogen replacing the oxygen.
Are they as stable or reactive as enolates? Do they aggregate in solution like enolates do?
Spectroscopic studies show that lithium derivatives of enolines can indeed exist as dimers in less coordinating solvents like toluene, but the equilibrium shifts towards monomers in better donor solvents like THF, especially at higher concentrations. The crystal structure of some lithiated enamines, like the N-phenylamine of methyl-T-butyl ketone, often found in Figure 1.6, visually reveals their substantial ionic character, with the lithium amication tightly associated with the nitrogen.
So they cluster too.
Yes, this tight association, similar to enolates, means their aggregation state can profoundly impact their reactivity and selectivity. Generally, anions are often more nucleophilic than enolates, making them highly efficient at reacting with alkyl halides, sometimes allowing for milder conditions. This increased nucleophilicity makes them particularly useful for alkylating aldehydes, which, as we discussed, are difficult to alkylate directly via their enolates due to the pervasive issue of competing aldol reactions.
Is their regioselectivity predictable, like the kinetic and thermodynamic enolates we discussed earlier?
For ketone iminogens, the regioselectivity is a bit more complex than with simple ketone enolates because there are two imine stereoisomers, and each of these can potentially form two regiosteric enamine anions. However, with strong, hindered bases like LDA at low temperatures, deprotonation often selectively occurs at the methyl group rather than a more substituted alpha carbon. Interestingly, the most stable, thermodynamically favored structures are typically the less substituted isomers, just like with enolates, often due to hyperconjugation. Again, the solvent, the metal counterion, and the degree of aggregation of the enamine anion all play a nuanced role in dictating the precise regiochemistry and stereochemistry. For instance, a thorough study of cyclohexanone anions revealed a preference for axial hydrogen abstraction during deprotonation, highlighting the importance of conformational effects even in this early deprotonation step.
Can you achieve enantioselectivity using these anions too, just like with the chiral auxiliaries for enolates? That would be incredibly powerful for synthesizing specific drug candidates.
Absolutely, and it's a very powerful strategy. This is one of the true highlights of imine chemistry. By preparing imines from enantiomerically pure chiral amines that already have a defined three-dimensional handedness, the new carbon-carbon bond can be formed with a strong bias for one specific stereochemical configuration at the newly formed chiral center. After alkylation, you simply hydrolyze the imine back to the ketone, and you're left with an enantiomerically enriched product.
So the imine acts like the auxiliary here.
Exactly. Comparative data, sometimes seen in Table 1.4, provides fantastic examples with very high enantiomeric excesses, sometimes exceeding 99%, demonstrating excellent control over chirality.
What's the key to that precise stereochemical control? How does the chiral amine dictate the handedness of the final product?
It often involves chelation, similar to what we discussed with chiral auxiliaries. For instance, a proposed transition state model, like TSJ, depicted in the textbook for an imine derived from 2-methoxyethylamine, shows the methoxy group on the chiral amine chelating with the lithium ion. This chelation creates a very rigid and well-defined structure for the transition state, effectively locking the imine anion into a specific conformation. This rigidity, combined with the steric bulk of other groups on the chiral amine, then dictates which face of the imine anion the alkylating agent approaches from, preventing attack from the sterically hindered side. The lithium ion's interaction with the leaving group of the alkylating agent also contributes to stabilizing this specific desired transition state, leading to a highly selective reaction. It's a testament to designing molecules to literally guide their own reactions. Finally, we have hydrozones, which are also derived from carbonyl compounds and amines, but specifically from hydrazine derivatives, meaning they contain a nitrogen single bond.
What are their advantages, or what makes them a distinct and valuable tool in the synthetic arsenal when compared to enolates or imine?
They offer a few key advantages that make them quite appealing for certain synthetic challenges. First, they are often more stable than simple alkylamines, which is a big practical benefit in synthesis, making them easier to handle, purify, and store without decomposition. Second, and crucially, they offer excellent regioselectivity in deprotonation. For example, N-dimethylhydrozones of methyl ketones are kinetically deprotonated specifically at the methyl group, regardless of the hydrozone's own stereochemistry.
So they reliably react at the methyl group.
Yes, which makes them exceptionally useful for two successive alkylations, allowing you to create unsymmetrical ketones with precise control over where each alkyl group is attached. This sequential alkylation ability is a powerful way to build complexity in a controlled manner.
Do they show similar stereoselectivity patterns in alkylation, like the other enolate analogs we've discussed?
Yes, they do. The anion of cyclohexanone N-dimethylhydrazone, for instance, shows a strong preference for axial alkylation. And the 2-methylcyclohexanone hydrazone yields cis-2,6-dimethylcyclohexanone upon alkylation. This is due to the two-metal group's pseudo-axial orientation on the hydrazone, which effectively shields one face, causing alkylation to occur on the opposite face, anti to the lithium K quotient. Even alpha-beta-unsaturated aldehydes, which are often challenging to alkylate, can be alpha-alkylated via their hydrazones, demonstrating their versatility and ability to tackle difficult substrates.
And for enantioselective control, creating a single mirror image, do hydrozones also have a trick up their sleeve, similar to the chiral auxiliaries?
This is where chiral hydrozones truly shine, and they've become incredibly important reagents in asymmetric synthesis, particularly those derived from N-amino-2-methoxymethylpyrrolidine. These are affectionately known as SAMP, and its enantiomer, RAMP.
SAMP and RAMP.
Catchy. They are, and they allow for highly enantioselective alkylation of ketones, often with excellent chemical yields and very high diastereomeric ratios. The crystal structure of the lithium anion of a SAMP hydrozone, like the one from 2-acetylnaphthalene, often seen in Figure 1.7, visually demonstrates how the lithium patient is beautifully chelated by both the exocyclic nitrogen of the hydrozone and the methoxy group on the auxiliary. This chelation locks in the precise geometry needed for stereochemical control, ensuring the alkylating agent approaches only from the desired face. After alkylation, these hydrozones can be gently converted back to the desired ketones using mild conditions that preserve the newly formed chiral center, preventing any loss of enantiomeric purity. Scheme 1.11 provides a wealth of examples, including alkylations crucial for synthesizing complex natural products like anti-alarm pheromones, antimalarial analogs, and epothalone analogs, showcasing their profound impact in pharmaceutical and natural product synthesis. It's a testament to how slight modifications in molecular design can unlock incredible synthetic power. Outro.
Wow, what an incredible journey into the heart of organic synthesis. We've truly seen how what might seem like a simple concept, breaking and forming bonds, is in fact an exquisitely precise science. From the fundamental act of deprotonation to the intricate dance of steric hindrance, chelation, and the clever design of chiral auxiliaries and solvent systems, chemists have developed an astonishing level of control. They're building incredibly complex and specific molecular architectures, one carbon-carbon bond at a time. It's like watching master builders at the atomic scale.
It's truly humbling and inspiring. From the historical development of malonate alkylations, which laid the very foundation, to the cutting-edge use of chiral auxiliaries that deliver single enantiomers, and the critical role of computational studies that predict subtle molecular behavior. This deep dive into Chapter 1 really highlights the creativity, precision, and relentless problem-solving inherent in organic synthesis. It's the bedrock for creating new drugs, developing advanced materials with tailored properties, and understanding fundamental biological processes. The ability to control not just connectivity, but also the precise three-dimensional arrangement of every atom is what makes it so uniquely powerful and essential.
It certainly makes you think about the possibilities, doesn't it? After seeing how chemists can orchestrate such precise transformations, what molecular structure would you try to build with these powerful tools, knowing you can control every subtle detail? Imagine the impact on human health, technology, or simply understanding the universe around us.
That's the beauty and the enduring appeal of organic synthesis. The ability to design and create new molecules with valuable, even life-changing properties, whether for treating disease, developing advanced materials, or simply exploring new chemical space, is a profound testament to the power of human ingenuity. It's about literally designing and building at the molecular level, creating something from scratch that has never existed before, but that can change our world.
That's all for this deep dive. Thank you for joining us on this exploration of advanced organic chemistry. We hope you feel a little more well-informed and inspired by the intricate and utterly brilliant world of molecular creation.